7.1 starts going over radicals. When you've looked at these radicals prior to today, you most likely have looked at radicals as in the square root. So you don't have an index, you don't have a little number on the outside of that radical sign. With these radical symbols, which is what you see here, you have something that's called an index. That index is that little number that is not in front of, but attached to that radical. With that index, it will tell you how many of the same numbers you need in order to complete that radical. When we do these radicals, or when we simplify them, we are going to be taking the we're going to be finding the prime factorization and looking at the index to see how many of the same number we need in order to pull one of those numbers out. Whatever does not pair up with the same number stays underneath the radical. So if we look at example 1, we're just finding the following roots. For A, we have the square root of 25. You don't see an index on the outside of that radical, so you don't see a little number that's attached to that radical, so it's automatically a 2. So you want 2 of the same numbers when you find the prime factorization of 25 in order to pull one of those numbers out to represent that. 25 is 5 times 5, so this is the same exact thing as saying the square root of 5 times 5. Again, we said that that index is an invisible 2, so we need 2 of the same number to pull one of them out. So our answer for this is just 5. For example B, we have the cube root of negative 27. Now, with this one, we see that we have a negative underneath that radical. The only time that it is okay to have a negative underneath a radical is if that index is an odd number. Odd numbers like 3, 5, 7, 9, so on. This index is odd. We do have a negative underneath that radical, so it's okay to do. If it was an even index, so like the square root, the fourth root, the sixth root, the eighth root, so on, then you would not be able to do it and just automatically be no solution. But because our index is odd, we can continue with this and find the cube root of negative 27. Because our index is odd and we have a negative underneath that radical, our answer is going to be negative. So I circle my negative to remind myself I need to include that with my answer. From there, we find the prime factorization of 27. 27 is 3 times 9. The 9 is 3 times 3. This cube root, or this index of 3, is saying that we need 3 of the same number in order to pull one of those numbers out to represent the cube root of that negative 27. You have 3 3s here, so we're going to pull one of those out. We're going to apply that negative to that, and our answer is just negative 3. For example C, we have the 6th root of 64. That 64, if we find the prime factorization of it, we have 8 times 8. 8 is 2 times 4, and 4 is 2 times 2. This is telling us we need 6 of the same number. So 2 times 2 times 2 times 2 times 2 times 2 is the prime factorization of 64. We do have 6 2's there, so we pull 1 out to represent all 6 of those, and the prime factorization of that 64 is just 2. Or sorry, the 6th root of 64 is just the 2. For example D, we have a negative square root of 64, so the opposite of the square root of 4. For this one, that negative is in front of that radical, so the only thing it's telling us to do is to multiply a negative 1 times the square root of 4. 4 is 2 times 2. That gives us our pair of 2 that we're looking for. So this is just negative 1 times 2, which is negative 2. For the next part of our lesson, we're looking at variables in these radicals. When you look at these variables within these radicals, you want to divide the power by the index. Whatever's left over stays underneath the radical. So if we look at the next section, example 2, we're just finding each root, and we're assuming that all variables can represent any real numbers. We're going to use absolute value symbols when necessary. I'm not going to worry about the absolute value The only thing that I want you to worry about is to make sure that you are dividing the power by the index. If there isn't an index, remember it's an invisible 2. So for example A, we have the square root of 2. Again, our invisible index here is 2. So this is the same exact thing as saying a to the second power divided by 2, which just gives us a to the first power, which is a. So the square root of a squared is just a. Whenever your index and your power are the same, they cancel each other out. So in reality, you could have said to yourself, my root or my index is 2, my power is 2, they cancel each other out. The only thing I'm left with is that a. For example, B, we have the square root of x to the 22nd power. So with this one, we don't have an index. It is an invisible 2. So we're just going to do the x to the 22nd power divided by the 2. So this is going to give us x to the power of 11. For example, C, we have the fourth root of w to the 40th power. So that root and that power are going to divide. So we're going to have w to the 40th power divided by 4. So the powers are going to divide. 40 divided by 4 is 10, so that's just w to the 10th power. For example, D, we have the cube root of t to the 18th power. Our index is 3, our power is 18, so we're just going to do t to the power of 18 divided by 3. So that leaves us with t to the power of 6. For example, E, we have the fifth root of s to the power of 30. So we're just going to be doing s to the power of 30 divided by 5. 30 divided by 5 is 6, so that's just s to the power of 6. The next part of this lesson that we're going to be looking at is our product rule for radicals. When we are multiplying radicals, as long as the index is the same for the radicals, we can multiply what's underneath them. And then again, if the radical is raised to a power, if the index and the power are the same, they cancel each other out. For example, 3, we're just simplifying each radical and assuming all variables represent non-negative real numbers. For example, A, we have 4y underneath the square root. So this invisible index is a 2, which means we're taking the square root of 4 and the square root of y. The square root of 4, we said 4 earlier, was 2 times 2. We pair up a set of 2 2's to represent, to pull 1 out. So that's just 2. However, the square root of y you cannot do because y is just y. It's not y times y, so you cannot pair up another y with the y. So you're going to be doing 2 times the square root of y. You just pull these together, and you have 2 square root y. So if you cannot simplify that radical, you just multiply them together and keep them attached to one another. For example, B, we have the square root of 3y to the 8th power. This is the same exact thing as saying the square root of 3 times the square root of y to the 8th power. Now the square root of 3, the prime factorization of 3 is just 1 times 3. You can't do anything with that, so it's going to stay the square root of 3. That square root of y to the 8th power, our index is 2, so we're going to do y to the power of 8 divided by 2, which is just y to the 4th power. Again, that square root of 3 is going to stay. We're going to multiply these together. If you remember from example A, that square root of y was last in our expression. The square root of any number or the root of any number that you have left over is an irrational number, which means it's going to go behind or after your rational term or your rational number. In this case, that y to the 4th power will go first, and then you put the square root of 3 right after it. So it's just y to the 4th power times the square root of 3. For example, C, we have the cube root of 125w squared. If you wanted to separate this, you can. It would just be the cube root of 125 times the cube root of w squared. To find the cube root of 125, we're going to find the prime factorization of it. It ends in a 5 or 0, so 5 automatically goes into it. 5 goes into 12 2 times with 2 left over. 5 goes into 25 5 times. The 25 is also 5 times 5. So we're looking for a group of 3 of the same number to pull 1 out. We have 3 5s, so that's just 5. The cube root of w squared you cannot do. That w squared is just w times w. You do not have 3 of the same term to pull 1 out, so it's going to stay the cube root of w squared. We multiply these two together, and we just have 5 cube root w squared. For our next set of examples, we're just simplifying each of these radicals. For example A, we have the square root of 12. With these radicals, we're not necessarily going to be able to take the complete square root of that number, the complete cube root of that number, so we are going to have numbers left over. That's fine. They just stay underneath the radical. So if we find the prime factorization of 12, 12 is 3 times 4, 4 is 2 times 2. So technically, the square root of 12 is the same exact thing as saying the square root of 2 times 2 times 3. Now we don't have an index here, so it is an invisible 2, which means we would need 2 of the same number to group up in order to pull 1 out to represent that group of that number. We have 2 2's, so 2 comes out. The 3 is left over, so it stays underneath the square root. So we just have 2 square root 3 as our answer. For example B, we have the cube root of 54. That 54 is 6 times 9. The 6 is 2 times 3. The 9 is 3 times 3. We're looking for 3 of the same number. We have 3 3's. We're going to pull one of those 3's out. That 2 is left over. It doesn't group up with another 2 2's. So we're going to keep that underneath the cube root symbol. So it's just going to be 3 cube root 2. For example C, we have the fourth root of 80. So 80 is 8 times 10. The 8 is 2 times 4. The 4 is 2 times 2. And the 10 is 2 times 5. So again, this is the same exact thing as saying the fourth root of 2 times 2 times 2 times 2 times 5. We need 4 of the same number to group them up. We have 4 2's. We'll pull 1 2 out. That 5 is left over. So it stays underneath the radical to give us 2 times the fourth root of 5. For example D, we have the fifth root of 64. 64 is 8 times 8. The 8 is 2 times 4. 4 is 2 times 2. Again, the 8 is 2 times 4. The 4 is 2 times 2. So this is the same thing as saying the fifth root of 2 times 2 times 2 times 2 times 2 times 2. We need 5 of the same number. So 1, 2, 3, 4, 5. We have 5 2's. We're going to pull one of those out to represent that group of 5. The one that's left over stays underneath the radical. So that's just 2 fifth root 2. For example 5, it tells us just to simplify each of these radicals and to assume all variables represent non-negative real numbers. So with these, we're going to be doing the same exact things that we did in the sections before. We're going to find the prime factorization of the number that's underneath the radical, and then divide the power that's on the exponent by the index. If there isn't an index, it's automatically an invisible 2. So for example A, we have the square root of 20x cubed. So again, our invisible index here is a 2. We find the prime factorization of 20. We have 4 and 5. The 4 factors out to be 2 and 2. So this is the same exact thing as saying the square root of 2 times 2 times 5. If you wanted to also extend that x cubed, you could by doing x times x times x. Or again, you can just divide the 3 by 2. You'd get 1 with a remainder of 1. So when x would come out of the radical and 1 would stay underneath. So from here, we would group up sets of 2, so pairs. The 2's group up, these x's group up. So the 2 you'll bring out, the x you bring out, underneath stays the 5 and the x. So it's just 2x square root 5x. For example B, we have the cube root of 40a to the 8th power. So again, we're going to find the prime factorization of that 40. We have 4 and 10. The 4 is 2 and 2. 10 is 2 and 5. We group up sets of 2. These 2's group, or sorry, sets of 3, not 2. Our index is 3, so we want a set of 3. The 2 comes out. The 5 stays underneath the cube root. That a to the 8th power, you're taking the cube root of that as well. So we're going to divide the 8 by 3. We get a to the second with the remainder of 2. So the a to the second is going to come out, and the 2 stays underneath. The a squared stays underneath. Again, if you wanted to take that a to the 8th power and multiply it out to be a times a times a times a 8 times, you could have done that. From here, we're going to multiply the 2 and the a to give us, or sorry, 2 and a squared to give us 2a squared. And then underneath the radical, the 5 and the a squared multiply together to give you 5a squared. So it's just 2a squared cube root 5a squared. For example C, we have the 4th root of 48a to the 4th power b to the 11th power. For this one, I'm going to first separate all of this. So I have the 4th root of 48 times the 4th root of a to the 4th power times the 4th root of b to the 11th power. So the 48, I'm going to find the prime factorization of it. I have 4 and 12. 4 is 2 and 2. 12 is 2 and 6. 6 is 2 and 3. We're looking for a group of 4. We have 4 2's here. So the 2 comes out. The 3 stays underneath the radical. So that's just 2 4th root 3. For the 4th root of a to the 4th power, we're going to divide those power, or the power, by the index. 4 divided by 4 is 1, so that's just a. For the 4th root of b to the 11th power, we're going to take that 11 as the power and divide it by 4. This is going to give us b to the 2nd power with a remainder of 3. So to bring this all together, this is going to be 2 times a, which is 2a, times b squared, which is b squared. Underneath our radical, we're going to have the 3 and the b cubed that's left over. So it's just 2ab squared 4th root 3b cubed. For example D, we have the 5th root of w to the 7th power. So we don't have any numbers here or coefficients of this w to the 7th power. So we're just going to take that 7, divide it by 5. We get w to the 1st power with a remainder of 2. So the w to the 1st power comes out. The w squared stays underneath the radical. So that's just w 5th root w squared. For the next part of our lesson, we're going to be going over quotients of radicals. When you have a root or a radical over a fraction, it's the same exact thing as saying that radical of the numerator over that radical of the denominator. And then you're just simplifying. So if we look at example 6 for a, we have the square root of 25 over 9. This is the same exact thing as saying the square root of 25 over the square root of 9. The square root of 25 is 5. The square root of 9 is 3. So 5/3 is our answer. For example B, we have the square root of 15 over the square root of 3. Now we can rewrite this using the product properties of radicals. This square root of 15 is the same exact thing as saying the square root of 3 times 5 over the square root of 3. That square root of 3 times 5 is the same exact thing as saying the square root of 3 times the square root of 5 all over the square root of 3. Now these square root of 3's can simplify and cancel out, so the only thing we have left is the square root of 5. If you did not do it that way, you would have to rationalize the denominator, which means that you'd have to multiply the top and the bottom of this fraction by the square root of 3. leaving you with the square root of 45 over 3. From there, you would then simplify as well. For example C, we have the cube root of b over 125. So this is the same exact thing as saying the cube root of b over the cube root of 125. That 125 is 5 times 25. The 25 is 5 times 5. We're looking for 3 of the same number, which we have. So that's just the cube root of b over 5. For example, D, we have the cube root of x to the 21st power over y to the 6th power. So this is the same thing as saying the cube root of x to the 21st power over the cube root of y to the 6th power. From here, we're just going to divide the power by the index. So we're going to do x to the 21st divided by the 3rd over y to the 6th divided by the 3rd. So this just simplifies to be x to the 7th over y to the 2nd. For our next example, we're just simplifying each of these radicals. So for example A, we have the square root of 50 over 49. Again, this is the same exact thing as saying the square root of 50 over the square root of 49. That 50 is 2 and 25. The 25 is 5 and 5. We're looking for groups of 2, so that's 5, square root 2, over the square root of 49 is 7. Your 5 and your 7 do not simplify, so it's just 5 square root 2 over 7. For example, B, we have the cube root of x to the 5th over 8. So again, this is the same exact thing as saying the cube root of x to the 5th over the cube root of 8. The cube root of that 8 is just 2. On the top, the x to the 5th, we're going to divide it by 3. So this is going to give us x to the 1st with a remainder of 2. So this is going to be rewritten as x cube root x squared over 2. For example C, we have the 4th root of a to the 5th over b to the 8th power. So this we're going to rewrite as the 4th root of a to the 5th power over the 4th root of b to the 8th power. That a to the 5th power, we're going to divide the 5 by 4. That b to the 8th power, we're going to divide the 8 by 4. So this gives us a to the 1st power with a remainder of 1 over b squared. That a to the 1st power with a remainder of 1 is rewritten as a times the 4th root of a. And then we have that b squared underneath it. So it's just a times the 4th root of a over b squared. The last part of our lesson goes over finding the domain of each of these functions. With these square root and cube root 4th root functions, you have to keep in mind the index. You need to remind yourself that if the index is even, so 2, 4, 6, 8, your answer or the number that's underneath that radical cannot be a negative. So it has to be greater than or equal to 0. If your number is odd, that's your index. It can be any number. So all real numbers would be your domain. When you find your domain for these, you are going to be writing them using interval notation. So if we look at example A, we have f of x is equal to the square root of x minus 5. Your index here is a 2. It's even, so it's got to be greater than or equal to 0. So we're going to take what's underneath the radical, so x minus 5, we're going to set it to be greater than or equal to 0 and solve for x. We're going to move the 5 over by adding it to each side, and we get that x is greater than or equal to 5. So our domain for this one goes from 5 and includes 5 up to infinity. For example B, we have f of x is equal to the cube root of x plus 7. With a cube root, 5th root, 7th root, any odd root, we can have any number, positive or negative, underneath that radical. So our domain for this one is all real numbers. So we're going from negative infinity up to positive infinity. And lastly, for example C, we have f of x is equal to the 4th root of 2x plus 6. Our index here is even, so anything that's underneath that radical has to be greater than or equal to 0. So we're going to take what's underneath the radical, the 2x plus 6, and set it to be greater than or equal to 0. We move this 6 over by subtracting it from each side. We get 2x is greater than or equal to negative 6. And then we divide each side by the 2. And we get that x is greater than or equal to negative 3. If x is greater than or equal to negative 3, that means our domain goes from negative 3, including negative 3, to positive infinity.